All right, we are back from a long fall break. Some of you have recovered, some have not. So we need to cover today second order ordinary differential equations. And we will not finish the topic until Wednesday, but everything that is on the slides is included in the exam regardless if I covered it or not. Okay, that's the deal. And as you know, it's part of the homework. So we will make an effort to address everything that I think is essential. So I'm going to jump to slide 9 and to define a second order differential equation with constant coefficients. So nothing special. Second order derivative you can see there, and the coefficients to start with, I'm going to take them to be constant. We're actually going to work with linear second order equations, which means in most examples, the coefficients A, B, C are going to be functions of time. But the methodologies will also be applied to nonlinear second order differential equations to some extent. Okay, what is the trick of solving these equations? You're going to try to see if a solution of the form e to the RT actually going to make the job, okay? By the way, in a lot of the homework problems that I have assigned you, this is how it's going to work. You're going to have to actually learn from the slides what the form of the solution is going to be. You try it. If it works, success. If not, you start guessing how to can generalize it from the obvious solution, okay? So in this case, the obvious solution is e to the RT. So if we plug it in and we take second order derivatives, what actually we get is we get the characteristic polynomial that looks AR squared plus BR plus C equal to 0, okay? And in principle, this equation can be solved. It's a quadratic equation with constant coefficients. So if we solve it, we have, generally speaking, two roots, and I'm writing them explicitly. And the type of solutions you get, because we said we try e to the RT, so the way the solutions are going to look, it all depends if b squared minus 4ac is equal to 0, if it is greater than 0 or less than 0. Okay? So nothing special. I'm sure you have seen this in your undergraduate studies. So basically, the type of cases we want to consider is we have two roots that are real and different, two roots that are real and the same. So when b squared minus 4ac equal to 0, you get two roots minus b over 2a. And then the interesting case when you have two roots that they are complex. All right, so when b squared minus 4ac is negative, you're going to get a complex number from there. So we will be interested to see how things look like in that case. So since we are just starting talking about differential equations of second order, so let's take the trivial case where we have two roots, and they're real, and they're different from each other. So basically, the solution looks as e to the R1t times some constant plus C2 e to the R2t. And by the way, I remind you that I am looking for the homogeneous equation. So there is nothing on the right-hand side. So basically, this is what we call the null solution, okay? And of course, you know, these two exponentials can either grow with time or decay, depending if R1 and R2 are positive or negative numbers. So let me do one initial value problem. So again, the homogeneous equation, all right, keep that in mind. So we're going to put some initial conditions, and since we haven't seen this before, this is a second order equation, so you need to have, if you think that y is the displacement, y prime the velocity, and y double prime the acceleration, you're going to have to provide initial conditions on the displacement and velocity. So that's what you see here. So time t0 would prescribe y and y prime. So we have two equations, which is good because in this general solution, we have two unknowns, C1 and C2. So actually, if you plug things in, all right, you are going to get, so you know, if you set at time t0, this is equal to y0. You get the first equation here. Then derivative at time t0 equal to y0 prime. You solve for C1 to C2, and there is the solution to the initial value problem. So for example, if I take this particular differential equation with roots -2 and -3, the solution looks like this, okay? And if you put some initial conditions, nothing major, you can solve for C1 and C2. I just need the final answer only. So the final answer will look 9 e to the -2t minus 7 e to the -3t. And if you want to plot, it looks like this. So we haven't really done anything, but we defined there is a characteristic polynomial. The solutions may be of the form e to the rt. When that works, certainly that works for the equation with constant coefficients. And then we came up with a general solution that is these fundamental solutions to the null space problem times some constants, and these constants are computed from the initial conditions. All right, so I need to be doing some jumping today. So we're going to jump to slide 19. I want to discuss the theorem, basically, that says something about the existence of the solutions to this initial value problem. So if the coefficients, if I write it in this form, where the first coefficient is equal to 1, and I generalize that these coefficients are functions of t, and I even have a forcing term. So if these functions, p, q, and z, are continuous in some open interval that contains the initial time t0, then there is a unique solution to this problem. The theorem doesn't say how to compute it, but effectively the only thing I want you to remember is if p, q, and z are continuous in some open interval that contains, this is very important, that's why I put it in blue there, it contains the initial time t0, then there is a unique solution in that interval. I want to be sure that the next slide is one we're supposed to cover. All right, so let's do this. All right, let's do this particular example. And I want you to tell me if a solution to this initial value problem exists, and in which interval. So by applying the theorem. And I remind you the theorem, the y double prime coefficient is equal to 1. So we're going to have to write this as such. So the coefficient p is going to be t divided by this. So it would be 1 over t minus 3. The coefficient q is going to be minus t plus 3 divided by that. And the right-hand side is equal to 0. So I want you to look at this, and with the initial time equal to 1, and tell me, do we have a solution to this problem? And in which interval? You remember what we need to show is that there is an open interval that contains time 1, times t equal to 1, where these functions are continuous. Can you tell me one such open interval? Uh, 0 to 3, okay. And I'm assuming 0 to 3, not including 0 and 3. Is that correct? All right. That's why it says an open interval. All right, so so this problem then has a solution, and we will see possibly today on how to actually compute the solution to this particular problem. Again, the theorem doesn't say anything on how to compute it, but it says if there is a solution to the problem. All right, so I'm going to jump to slide 23. So the example we started, right? We computed two solutions to the null space problem. You remember it was e to the rt, where are the roots of the quadratic polynomial that we considered with constant coefficients. But here I'm assuming a the more general homogeneous problem with the coefficients being a function of time. So let's say that we compute two solutions, y1 and y2. Will you agree with me that if I take a combination of y1 and y2 for this linear problem, this combination will also be a solution? Right? If y1 and y2 are solutions of this, will you agree with me that this combination will also be a solution? What do you think? Right? So that is obvious. But let me so say the following thing. Suppose that I have some initial conditions, y at time t0 equal to y0, and the derivative at time t0 equal to y0 prime. So can you tell me if this is still a solution, or under which conditions this can be a solution? So before we had no initial conditions. Now I bring in initial conditions. So what I'm asking you is, OK, this looks like, seems to satisfy this equation. But now if I have these initial conditions, under which conditions you can guarantee for me that this y satisfies these initial conditions? Well, let's try it, right? So y is the combination of y1 and y2. So the y0 is going to be equal to this, right? And if I take derivatives of that, y0 prime is going to be what is given on the left-hand side of the second equation. Nothing fancy. So look at those two equations and tell me under which conditions this solution y satisfies the initial conditions. What needs to happen for the solution y to satisfy the initial conditions? Here I have a system of two equations with two unknowns. So what do I need to guarantee that this system has a solution? I know I'm asking stupid questions, but you know, lots of the things we do in this course, in some sense, are stupid and easy. On the other hand, are mysterious because it seems when we have an exam, lots of these things, they're not in your minds, right? So under which conditions we can guarantee that there is a y, that these two equations are satisfied? Linear algebra. I never heard of that word. I don't remember I mentioned it in linear algebra. You are reading the lectures ahead of me, so before we even said anything about that W guy or lady, since I don't know the history, in linear algebra, what is the condition that we need to have a solution? The determinant there has to be, I mean, that matrix of coefficients have to be invertible, right? So the matrix that is, has on the first row y1 and y2 at t0, and on the second row y1 prime and y2 prime has to be non-singular. And that matrix is what we call the Wronskian, or something like that. Right? And here is that matrix. OK? So we need to guarantee that this W is not equal to 0. OK? Now, you will see that this W is coming out actually in other methods later in the lecture today. But a first sort of touch with this W is to guarantee that this combination of the fundamental solutions satisfies the initial conditions. That's where W is coming in. OK? So, and again, this will come up in other methods that indicates that this is a little bit more fundamental than what you see on this slide. OK, and so how do you compute this? If you already have y1 and y2, you can take the derivatives, compute the determinant. And the whole idea is actually to find some time t0 where you can claim it as the initial time that this thing is non-zero, okay? But if time t0 is given, then you plug in everything at this particular time t0, and you make your decision based on that. Let me go to slide 27 and do a particular example. So in this problem, if you solve the fundamental, the polynomial, you have s squared plus 5s plus 6 equal to 0. I am guessing it has roots -2 and -3. So the fundamental solutions are e to the -2t, e to the -3t. The derivatives are this and that. So you compute the determinant, and it comes to be minus e to the -5t. Right? Is that, can I put initial conditions at any time for this problem? Is that Wronskian equal to 0 at any t? Nope. OK, so we're safe. All right, so we covered that. So this, again, guarantees basically that this combination of the fundamental solutions gives me a generic solution to the differential equation. OK, I'm going to do a major jump now. There is nothing in between, more examples. And I'm going to discuss the solutions to the second order equation when the solutions come to be complex numbers. So let me put everything up. OK, so I'm going to start again with the case of the coefficients being constant. All right, so they're A, B, C. We try, remember, e to the RT as the solution. We get the characteristic equation. We solve it. So we're going now to assume that b squared minus 4ac is less than 0, which means that the solutions we get are of the form of minus b over 2a, which I call here lambda, and then plus minus I times mu, where mu is basically the square root of 4ac minus b squared divided by 2a. So again, the details are not important right now. There is a real part that I call lambda, and there is an imaginary part that we call mu. So the fundamental solutions are e to, again, RT, but RT is lambda plus minus I mu. So the solutions have a term e to the lambda t, both of them, all right, that can grow or decrease with time depending if lambda is positive or negative. And then they have these exponential terms, e to the I minus mu t and e to the minus mu t. So what type of solutions are those? When you hear e to the I mu t, what is, remember Euler's formula? What is e to the I mu t? It's cosine of mu t and plus I sine of mu t. So it's an oscillation with frequency omega, with frequency mu. So in reality, instead of using these complex solutions the way that you see here, what you can do is, and let me see if I can jump directly to the correct slide. What you can do is you can use those two as the fundamental solution. Would you agree? Right? There is discussion in the notes that I can take combination of this and that, and eventually you come up with this. But come on, we are graduate students. We have common sense. So e to the lambda t cos of mu t and e to the lambda t sine mu t are the two fundamental solutions. OK? Nothing fancy. And again, someone will ask you, again, can you guarantee that the Wronskian here is non-zero? And if you plug in those two fundamental solutions and their derivatives in W, you actually get that this is mu e to the 2 lambda t. And because we assume here mu not to be 0, W is not 0. So we're OK. We can take any time as the initial condition. So the general solution is given by this nice formula. So if somebody gives you initial velocity and displacement, you can calculate coefficients C1 and C2. And again, here is an example. If you form the characteristic equation, You get two roots, real part minus 1/2, imaginary part plus minus 3i. So the two solutions look like this, all right, with coefficients that you see C1 and C2. And I don't know if we have any initial conditions. Yeah, so if your initial conditions are given like that, all right, you just have to plug in t equal to 0 and also evaluate the derivative at t equal to 0, solve for C1 and C2, and there is the answer. Okay? And obviously, you can see the nature of the solutions that you get with this type of complex roots. Obviously, you get exponential decay, all right? But as the solution exponentially decays to 0, it oscillates with frequency with omega equal to 3. So it looks like this, all right? So eventually it goes to 0, but in an oscillatory manner. And this is typical for all of these problems that you have this case of complex roots. Okay, so this is slide 45. So let me go to slide 46. Actually, I don't really care about slide 46. Sorry, wrong. So let me, there is a whole new section that I try to separate in the slides on vibrations. So we're going to revisit a lot of the things we do now in the context of mechanical vibrations, but I think it's also a good time to bring it here since we discussed about second order equations with constant coefficients. So here what I have is I have a case, an equation that looks like this. So obviously, this is an oscillator with mass m and a spring constant k. There is no damping. So if you put a solution to the form e to the rt, you really, why does the solution look like that? Can somebody tell me now what happened? So when you compute the roots, what type of roots you get in this problem? Before we had roots that had real and imaginary parts. When you compute, the characteristic polynomial of this will be mr squared plus kr. No, I'm sorry, mr squared plus k equal to 0. So what solutions do we get? Do we get solutions that have real and imaginary part, or what? Just imaginary, right? So that exponential we had before doesn't exist. And what we get is we get cosines and sines. And you can see, if you drop the m on the other side, you get basically the solutions are plus minus square root of k over m, all right? And k over m is the natural frequency. And if you put initial conditions y of 0 and y prime of 0, then a general solution looks like this. And you can see from this picture on the right, you get a pure nice oscillation without any damping. So keeps oscillating forever, okay? And again, we will see in more details mechanical vibrations, so we can relate this with other courses you may take in your studies. Okay. So let me jump. I like jumping today on slide 49 to discuss this concept of repeated roots, okay? And the method that goes with the name reduction of order. And let's see what slide was that, 49. So I'm going to go to slide 50. All right. So we're going to take the generic solution e to the ERT, but we're going to assume something particular, that b squared minus 4ac equal to 0. So basically, R1 and R2 is minus b divided by 2a. Okay? So obviously, because we have two initial conditions, we need two fundamental solutions. This is a second order differential equation. And here we see that R1 and R2 are the same. So we only have one solution that looks e to the minus b over 2a t, okay? That's not good enough. We need a second solution. So how does the second solution is going to look like? I can tell you what the answer is going to be because a lot of times you will save a lot of effort by knowing how things look like, and you try it, and if it works, you're done. But I'm going to tell you the methodology on how, for example, if it happens that the coefficients are not constant, the solution that I'm going to ask you to try will not work. The methodology will work. Okay? So again, the obvious solution for constant coefficients would not work when a, b, and c are functions of time. So what do you do? So one solution looks like e to the minus b over 2a times t, okay? So we're going to try a second solution that looks like some function of t times e to the minus bt over 2a. This concept is going to work for any case where you have the same R1 and R2, okay? I can tell you so that we can save time. If it happens that the coefficients are constant, v of t is going to come to be what? Since you read the notes. Is equal to t. All right? So v of t is going to come equal to t. If, however, the coefficients are not constant, but some functions of t, who knows what it's going to come to be? All right? You're going to have to come up with some differential equation for v, solve for v, and then y2 is going to be given by this nice equation. So how do you come up? Let's, do the very general case. How do you come up with a differential equation for v of t? All right? So v of t is unknown. So e to the minus bt over 2a is the first fundamental solution, and we multiply by some unknown function v of t. So the idea is, this y2 of t has to satisfy the differential equation. So you are going to plug in the differential equation, which means you're going to compute the first derivative of this, and then the second derivative of this, and that will give you a second order equation for v. But that equation is going to be simple because this other term that multiplies with v satisfies already the differential equation. So there will be a lot of cancellations. Can you see that? E to the minus bt over 2a, it's already a solution of the equation. So when you do the algebra, a lot of terms will cancel out. So in this particular case, right, so if you go and you say, this is y2, this is the derivative of y2 prime, this is y2 double prime, and you plug in all of these things in the differential equation, after some trivial algebra, nothing there, this is the equation that you get. As a matter of fact, I don't know why I did not cancel this term, because b squared minus 4ac is equal to 0, isn't it? Why it's equal to 0? Because the case we consider is equal roots, right? And b squared minus 4ac equal to 0. So in this particular case, v of t it's a linear function in t. And which means that y2 is a linear function in t times this fundamental solution. And this term alone, right, k4 times e to the minus bt over 2a, is nothing different from this solution. So we don't really need k2. So what we need to keep is t e to the minus bt over 2a. That's it. So basically, if the coefficients are constant, in addition to the e to the minus bt over 2a, immediately try, without any proof, try t e to the minus bt over 2a. All right? If now the coefficients are functions of time, do the general methodology and derive a differential equation for v, and then v times the first fundamental solution will give you y2. All right, and you can actually check, it's a good idea to do this in all of these problems. to be sure that you're not in trouble. So if you calculate the Wronskian, you can see that it's nowhere equal to 0. So this is actually a very good set of fundamental solutions, okay? They do the job, so you can solve initial value problems. All right, so what I have is here, I have this general proof that I highlighted. So let me put the whole thing up, okay? How you apply this reduction of order method. Once you have 1y1, you look for a solution that's of the form v of t times y1. So you compute the first derivative, you compute the second derivative, you plug things in here, and look immediately why I said things are simplified, because y1 double prime plus py1 prime plus qy1 is equal to 0, isn't it? Because y1 already satisfies the differential equation, the homogeneous equation. So the solution for v that you need to solve is y1 v double prime plus this times v prime equal to 0, all right? And how are you going to solve that equation? I mean, it looks like a second-order equation, but it is a simple second-order equation that you can solve it as a first-order equation. How can you solve it as a first-order equation? How you can compute v from this equation? Set v prime equal to some function u of t, all right? Then this becomes a first-order equation in u. Solve for u, and once you solve for u, you can go back and compute v, okay? So you basically set v prime equal to u. So once you compute u, then you have to integrate that to compute v. And I give you a nice example, and I think I gave you things in the homework set as well. So in this problem, the coefficients are not constant. So I tell you that one solution is t to the minus 1, right? So, I mean, I could have easily not given you that information, but then you may not have been able to guess that one solution is t to the minus 1, okay? So here it is given. So you are looking for a solution v of t times t to the minus 1. So take first derivative, second, plug it in, and this is what you get. All right, so set v prime equal to u. So this becomes tt u prime. All right, can you solve this equation? Can you solve this last equation? 2t u prime minus u equal to 0. It's a first order equation. And actually it's a separable equation. Right, you can write du over, I mean, I can see there du over u is dt over 2t. Can you see that? It's a separable equation. So you get some logs when you do the integration, and once you compute u, you can integrate u to get v. And the answer basically for this problem, u comes to be t to 1/2, all right? So v, if you integrate, v comes to be t to 3/2. And if v comes to be t to 3/2, and we don't care about this constant term k there because it will give us the original solution t to the minus 1. So t to 3/2 times t minus 1, we get t to 1/2. And the solution to this y2 comes to be t to 1/2. And the Wronskian is non-zero. And this is how the nice solution looks like. C1 times t to the minus 1 plus C2 square root of t. That's not bad, right? I know we did it very fast, but again, there is really, what is the whole method, right? I want you to remember the whole method is you try a solution that has the form v of t, some unknown function of t, times t to the minus 1, and t to the minus 1 is the one fundamental solution you already have been given, okay? So we have generalized this concept from the case of equal roots to a situation where we have these coefficients that they're time dependent, I can still do the same methodology, and I can compute this V of t so that y2 is the second fundamental solution. All right. So now what I want to do is I want to discuss non-homogeneous equations. So there is something on the right-hand side. And I'm going to take you through a lot of possibilities when the right-hand side, it's a simple function. So if we have this with constant coefficients, we're going to address situations where the right-hand side is exponential functions, sines, cosines, polynomials, or sums or products of these easy functions, okay? So there is a laundry, basically, of formulas that you should immediately know how the solution looks like if G is one of these simple functions, okay? So let me go through this situation. Can you guess what is so the idea is to these problems, right? When you have a non-homogeneous problem, the general solution will be the solution to the homogeneous problem, which is what we already discussed, C1 times Y1 plus C2 times Y2. All right, so the homogeneous problem will be with the right-hand side being equal to 0. And now we're looking, I'm only going to emphasize the particular solutions to this problem. So can you tell me what type of particular solutions you will look if the right-hand side is t, or in general a polynomial? I mean, the idea is to assume something with some coefficients, plug it in the equation, and compute these coefficients and see if it does the job. So if the right-hand side is t, what coefficient do you think may do the job? I mean, what particular solution you think may do the job? This is a very simple case. Just guess. What order? We don't want to overkill it. First order. So how about if we try a solution that is alpha t plus b? All right, I'm sorry, or alpha plus bt. Okay, the same thing. So if you assume a particular solution that looks like this, so the derivative is this, and the second derivative equal to 0. If you plug it in, you can compute the coefficients, and then the particular solution is -1 plus t. So you can do this actually for any polynomial, right? If you have a quadratic polynomial, then you will assume that the particular solution is a quadratic, so it will be a plus bt plus c times t squared. You plug them in, and you compute ABC, hoping that it will work. And it will work if the coefficients are constant. Okay? All right. Give me a particular solution to this problem. What would be the obvious thing to try? Constant coefficients again. Yeah, so some constant, e to the 2t. All right? Some constant e to the 2t. So a e to the 2t, if we plug in all the derivatives, there is the solution. Done. Okay? How about this? And so how about this? So if you try something that is a constant time sine, you will see it doesn't work. And the reason it doesn't work, right, because when you take second derivatives, you will get sines back, and this will give you cosines, and this will be sines. So you're not going to have any cosine on the right-hand side to match the cosine that you get from the first derivative. So the solution you have to try when you have a sine is a combination of a sine and cosine. Okay? I mean, just, again, simple common sense type of things, and you hope for the best. If you plug them in, you can actually compute A and B, and there is the solution. Done. Okay? I mean, I'm not going to spend 2 hours to tell you all the algebra, to type these equations, right? So how about now t sine of t? Let's make it interesting. Give me a particular solution, t sine of t. You remember before, when we had t, what solution did we try? We try linear at plus b, right? Or something like that. And for sine, we try what? A sine of t plus b cosine of t. So what should I try now? I am going to try the product of the two solutions that I had before. So a plus bt cosine of t plus c plus dt sine of t. If you don't do this, right, so if you don't have both cosines and sines, it will not work. If you put the same coefficients on both, it will not work, okay? So cosine and sine has to come with their own independent linear function of the front. So if you plug it in, right, and you match the sines and cosines and the t times sines and the t times cosines, and you should do this algebra by hand to verify that you can do it, nothing major, the solution comes to be 2 minus t cosine of t sine of t. And that's slide 74. And now we're going to slide 75. I love this. It's so fast. How about e to the t cosine of 2t? Help me. E to the t cosine of 2t. We already said for e to the t, what do we try? For e to the t, what do we try? Before? A times e to the t. And for cosine, we try a cosine plus b cosine. So what is the solution? Will be exactly what we had before. So a times e to the t cosine of 2t and b to the t sine of 2t. Okay? So I don't have the case of the linear function with two coefficients. So all the coefficients are merged on a and b. And when you plug them in, surprise, surprise, it works, and that's the answer. All right? And that's slide 75. Now, I want you to tell me, no, come on. I want you to tell me a particular solution to this problem. You notice now it has sums of right-hand sides that we already have discussed. So you're going to have to use a simple idea here, that if somehow you can find particular solutions corresponding to each of these terms separately, then the sum of these particular solutions will also be a particular solution to the whole problem. Right? So can you find me a particular solution when the right-hand side is 3e to the 2t? What form will it have? A to e to the 2t. Can you find something for sine of t? It would be b sine of t plus c cosine of t. Can you find e to the t cosine of 2t? Yeah, it will be a coefficient, let's say, e times e to the t cosine of 2t plus f e to the t sine of 2t. So if you set these three problems, all right, and the general solution comes to be this wonderful equation. And so expect to see something like that in the exam for sure, because I'm really running out of ideas what to write, and I don't have any time. So it will be some stupid, simple calculation that gives you a solution that looks like that. OK, so this is slide 77. And let me jump to something more interesting. All right. There is a simpler example before that talking about resonance, but I want to go, because we're running out of time, directly to the fundamental derivation of this, okay? So let's say we want to solve this for an exponential solution e to the st, and you told me, right? You told me that the general solution you're going to try, will be a constant e to the st, right? Didn't you tell me a few minutes ago that the solution you will try will be a times e to the st? All right. What will be the answer for a when you plug it into the equation? So give me what a is going to be. Or I call it d, will be this. Right? Yes? Now, let's take an extreme situation and that this s on the forcing term, so the frequency of the forcing term, is the same as one of the solutions of the characteristic polynomial. Let's say the solution, this has two solutions. Let's say that s is equal to s1. So then d is equal to what? If s is equal to s1, what is d? D is infinity. So obviously, e to the st cannot be a solution in that case. Cannot be a particular solution because it blows up. Again, I took a coefficient e to the st for s being some constant. I said this is what we said before. That's the general particular solution. So d is given by that. But if that s happens to be one of the solutions of the characteristic polynomial, then d goes to, it becomes infinity. And we're in trouble. E to the st is not a solution. What do we do? E to the st is not a solution. So obviously, if you know tricks, you say if e to the st is not a solution, maybe t e to the st will be a solution. And you may be lucky, but the way I want to do it is I want to do it more formally with a little bit of algebra. So you know what I'm going to do is I am going to modify the solution d e to the st and take a particular solution of this form. Will you agree with me that this is also a particular solution and why? Look at this equation, y of t, and tell me if it is still a particular solution. I have not forced yet that s is equal to s1, but looking at that equation, do you think it's still a particular solution? Obviously, the first term, right, e over to st divided by that is a solution, right? This is what we have shown before. Now, the second term is a solution also. Why? It's a solution to what problem? E to the s1t is still a solution, but what problem? I don't hear you. To the homogeneous problem, to the null problem. All right? So e to the s1t is a solution to the null problem, so this is the correct solution. And you notice now, when s goes to s1, the numerator becomes 1 minus 1, and the denominator becomes 0. So you have 0 over 0. And then you use L'Hopital's rule. Right? And what is L'Hopital's rule? That this y of t as s converges to s1 converges to the derivative of the numerator with respect to s, all right, which is t e to the st, and you take the limit s equal to s1, and the denominator, basically, you get 2a s1 plus b. So immediately you can see that the correct solution when you have this resonance is t e to the s1t. Nice proof, right? Can you see that? Now, if you had guessed it and you write it down, I'm going to be happy. But this is a formal proof, actually, that this works, and it comes from L'Hopital's rule, and I like it. OK, I have 2 slides to go. So let's try it extremely rapidly. So let's take, this method is called variation of parameters. So let me put everything up so we can finish it in less than 2 minutes. So we have this equation with coefficients that are functions of time, including a forcing term. So the variation of parameters is going to try a combination of the fundamental solutions for the non-homogeneous equation. But this combination is going to involve functions u1 and u2. All right? So this is how this method works. If you have two solutions, y1 and y2 of the homogeneous problem, a general solution will be given by this nice formula. But you have now two unknown functions to compute. So you need to derive two differential equations. Two differential equations. Here is the way you're going to do it. If you take derivative of y prime, all right, you are going to get 4 terms. And one of those terms is going to be u1 prime y1 plus u2 prime y2. You agree with me? Two of the terms you will get will be that. So we force that to be equal to 0. This is how the method works. So we're going to force that u1 prime y1 plus u2 prime y2 equal to 0. And then, so we compute y prime with this equal to 0. And then we compute y double prime. And then we plug everything into the differential equation. You have to trust me. Second equation you get is the second equation that you see there. u1 prime y1 prime plus u2 prime y2 prime equal to g. And you say, what happened, when you take all these derivatives, there are too many terms. Why they have been canceled? Well, they have been canceled because y1 and y2 satisfy the homogeneous equation. So there will be 6 terms that will cancel out because y1 prime plus py1 prime plus qy1 equal to 0. And then the same thing for y2. So the equation that you get when you plug in y prime and y, the second equation is this. So there is your 2 equations with 2 unknowns for the 2 functions, u1 and u2. Again, the first equation, it's a constraint that defines the method, right? We're looking for solutions that satisfy this constraint. The other is what you get from the differential equation. So if you solve for u1 prime and u2 prime using Kramer's rule, basically, u1 prime comes to be equal to that, and u2 prime comes to be equal to that. And when you integrate, u1 and u2 come to be these nice integrals. All right? And suddenly, you have in an integral form the solution to this equation with arbitrary coefficients given in terms of these integrals. So if you can compute these integrals, you're done. All right? You're done. And here's one example. All right? If you take, actually, this is not an example. The time is going to come out on me here. But let me just say, and you go and you read this slide, OK? If I take that the solutions to the homogeneous equation is e to the s1t and e to the s2t, and you apply this method of variation of parameters, if you compute the Wronskian for y1 and y2, and you plug into the solution in integral form, it comes out that the general solution is given by the impulse response times the right-hand side of the differential equation f of t. And what is the impulse response? Is something you're supposed to compute in your homework problem. So if you don't get that nice answer, the impulse response being this difference of these exponentials divided by s2 minus s1, you must have some typo in your calculation, OK? And basically, I can use the impulse response to write the response to any right-hand side with this convolution the way that you see here. And this variation of parameters gives me this general solution. All right. So we will continue on Wednesday, mainly reviewing simple ideas of mechanical vibrations, OK? And then we will be done with this lectures on second-order ODEs. Yeah, because I'm nice. But the next